Hey friends, Dr. Borole is here. Today we will continue our discussion of logic gates and logic circuits. The logic circuits are broadly divided into two groups, sequential circuit and combinational circuits. The sequential circuits are flip-flops, counter, shift register. There are so many other categories, but as per the focus of basic electronic engineering, we study flip-flops, counters and shift registers. In combinational circuits, we will study adders, decoders, comparators, and multiplexers. Out of this, in combinational circuit, the main focus is on adder and subtractor only. Now let us see what is a combinational circuit. A combinational circuit is the circuit in which the output of the logic circuit depends on the values of input at that point of instant, that is present state. It does not depends on the order or sequence of applying the inputs. Whereas in sequential circuits, the output of the logic circuit depends on the state of inputs at the present time as well as the sequence in which the inputs are applied and the previous state of that input. The important topics of comparisons are shown here between sequential and combinational circuits. If we compare from the output dependence point of view, the combinational circuit output only depends on the present states, whereas the sequential circuits, the logic output depends on present state as well as the past states of the inputs and outputs. The combinational circuit not have any memory of the previous states, whereas sequential circuit mostly have the memory of previous state. That is the previous state of the variable. From the clock input point of view, in combinational circuit, clock is mostly not required, whereas sequential circuit works with the external stable clock, and at the edges or various states of the clock, the various operation sequence is taken place. The examples of combinational circuits are adder, subtractor, code converters, and so on. Flip-flop, shift registers, and counters are the examples of sequential circuits. Let us see the combinational circuit in your syllabus. We will see binary adders. Binary adders are of two types, half adder and full adder. Half adders are also called as 2-bit adder, and full adders are called as 3-bit adder. A typical block diagram of half adder, that is 2-bit binary adder, is shown in the figure here. A and B are the two inputs to the half adder, and the outputs are sum output and carry output. The truth table of half adder is shown. When both the inputs are 0, the sum is 0 and carry is also 0. When A input is 0 and B input is 1, the sum of the two is 1 and carry is 0. When A is 1 and B input is 0, then also sum is 1 here and carry 0. Then we will see last combination when both A and B are 1. A and B are added to each other, the sum will be 0 and carry output will be generated to 1. If you see this expression by observing the truth table, we can write the logic expression for the outputs sum and carry. We have already seen how to write the expression from the truth table. I will recall you. Let us consider the sum column. If you want to write the expression for the sum output, then in this column, for first row and last row, the output sum is 0. So ignore these rows altogether. And then for second and third row output, write the output terms. The first term corresponds to row 2 is A bar B, and for third row it is A B bar. So in writing the terms of output, first we will discard the rows corresponds to output 0 and then write the terms of input which presents the output corresponds to that row. So in this second row, A is 0, so we will take A complement, and B is 1, therefore we will take B. So first term will be A complement B. And in the third row, A is already 1, so we will take the variable as it is. B is 0, therefore we will take B complement. Now try yourself for the carry output. In carry output, first three rows are 0 here. And therefore we ignore those rows. Take the last row. Here you will see the input combinations are A equal to 1 and B equal to 1. And therefore, we will take C is equal to A and B. That is equal to carry. If you see this expression for sum, it is nothing but a exclusive OR operation that is denoted as A exclusive OR B. And carry operation is the AND operation of the two variable A and B. Now from this expression, we have to draw the circuit of the half adder. We have already seen how to draw the circuit using expression. So let us use that logic again and draw. Take the two variables A and B here. Connect these two inputs to the input of the exclusive OR gate. So you are getting the output of exclusive OR gate, that is S is equal to A bar B or AB bar, and therefore here you are getting the sum of the two bits. Again take the two inputs A and B and AND it. You are getting the output of AND gate C is equal to A and B, and that is nothing but the carry bit. And therefore, as we have seen the diagram of the half adder, block diagram of half adder, in this block you will have this circuit of exclusive OR gate and AND gate that generates sum and carry output. Now let us see the next adder. Whenever you are adding multiple bits, normally while adding two multi-bit numbers, we require to add 3 bits simultaneously. input 1, input 2 and carry from the previous column. So in that case, full adder is required. Let us see. The two inputs are A and B. Those are the two single input bits. And C is the third bit. It is connected to a full adder circuit. Full adder circuit generates the output, which is a sum of two inputs, and add the carry input in that sum. And final sum is generated as sum output here. Whereas if any carry is generated in this 3-bit addition, that is denoted by C0 output. Let us see the truth table now. We have three input A, B and C. We call C input as a C in, because in addition normally this is the carry from the previous column. Okay. Or simply consider as a third bit. And two outputs, we have sum as S and C0 as a carry. So there are 8 combinations of A, B, C exist. And the sum is shown here. So let us see the first row. A and B 0 and C bit is 0. Then sum is 0, carry will be 0. When A and B 0, so partial sum is 0. Add this C in that. So you are getting sum equal to 1 and carry equal to 0. Now A is 0 and B is 1. So add it. 0 plus 1 is 1. Sum is 1 and add C in that. So add 0. So you are getting sum equal to 0 and carry equal to 0. Now next row. Add A and B here. So 0 plus 1 is 1 and add now in that 1 the next bit C. And therefore 1 plus 1, 1 0, that is sum equal to 0 and carry will be 1. Now next combination, here A is 1, B is 0 and C is 0. So 1 plus 0 is 1, plus 0 is sum equal to 1 and carry equal to 0. Next combination, A is 1, B is 0 and C is 1. So we will have 1 plus 0 is 0, plus 1 is say 1 0. Means sum is 0 and carry equal to 1. Now next row, A is 1, B is 1. So 1 plus 1 is 1 0. Plus 0 is 1 0 again. So 1 0 means sum is 0 and carry will be 1. Now consider the last where all the inputs are 1. So 1 plus 1 is 1 0. Plus 1 is 1 1 means the sum is 1 and carry is 1. So that is the truth table of adding 3 bits. Now if you want to write the expression for the outputs, then as usual we will use the common logic, in which we will drop the rows corresponds to 0 present in the output. Let us consider the sum column. We will ignore row number this 1, 4, 6 and 7 corresponds to 0. Now we have to write the mean terms present in the output corresponds to the sum equal to 1 output rows. So here you will see second row. A is 0 means we take A complement, B is 0 means again B complement and C equal to 1. So A complement, B complement and C, that is the first term we have to read. Now go for the next row, third row. Now you write yourself. A is 0, means take a complement of it, that is A complement. B is 1 means as it is B, and C is 0 means C complement. And therefore, the term corresponds to this third row is A complement, B, C complement. Then take the fifth row. A is 1, B is 0, and C is 1. So the term corresponds to this S equal to 1 is A, B complement, C complement. Now 6th and 7th row is 0. Go for the last 8th row where sum equal to 1 and ABC inputs are all 1. And therefore, the term corresponds to this sub output is ABC. And therefore, here the term shown ABC. So there are 4 terms of all 3 variables present. You can directly implement this expression, but the circuit will be bigger. So first simplify this expression and then implement the logic circuit. From first 2 terms, take C in common. You will get in bracket A bar B bar or AB. A third and fourth term, take C in bar common. From term number 1 and term number 3, you can get C in common, and in bracket you will get A bar B bar or AB. And from second and fourth term, take C in bar common. You getting A bar B and AB bar. Whereas A bar B bar or AB is exclusive NOR gate, and A bar B and AB bar is the exclusive OR gate. Exclusive NOR can be converted to exclusive OR just by taking a NOT operation of exclusive OR. And therefore, we will have a exclusive OR operation here and we will take a complement of it. That becomes basically a exclusive NOR gate. And this second term remains as it is. So from this term, you will see the bracket terms are both exclusive OR. Take it common. So A exclusive OR B into C in is the first term, and C in bar is multiplied by A exclusive OR B. Now if you see this expression, consider C in as one variable and the bracket as a second variable. So it is exclusive OR operation of C in exclusive OR with A exclusive OR B. So ultimately, when 3 inputs are exclusive OR, you are getting sum. Now let us see the table of carry. It's shown here. The carry outputs are 1 for row number 4, 6, 7 and 8. So let us write the term present in the product output C0. Consider the fourth row where the C0 output is 1. Input A is 0, B is 1 and C is 1. So write the product term A bar BC. That is the first term here. Now go to sixth row. The inputs are A equal to 1, B equal to 0 and C equal to 1. So therefore, the product term present in the final product output C0 is A B bar C. Similarly, for the next row it is A B C bar, that is the third term. And for the last row it is A B C. Right. Now simplify this expression using Boolean theorems to reduce the implementation of the circuit. Here from first 2 terms we will take C in common. So in bracket you are getting A bar B or AB bar, that is the exclusive OR operation. And from third and fourth term, we will take AB common. So in bracket, you are getting C in bar or C in. So ultimately, when any variable is ORed with itself, that is C in bar or C in equal to 1. So C bar or C in is 1, and therefore we get A bar B C in or A B bar C in or AB. Now we will multiply the last term AB by 1 plus C in. Any term multiplied with any variable or 1 is 1, and therefore 1 plus C in is basically 1. Now distribute this AB on this bracket. So you are getting AB and ABC in. Now from first term and the last term here, we will take BC in common. So in bracket remains A bar and or A. So A bar or A is 1 again. The remaining term can be written as it is AB bar C or AB. Simplify next. So we come to this term already because A bar or A is 1. Now again we will substitute 1 equal to 1 or C in and multiply it with AB. After multiplication by AB, we are getting AB or ABC in. Now from second and the last term, take AC in common. In bracket remains B bar here and B. So B or B bar. B or B bar is equal to 1. And therefore, final carry output is AB, this one, plus AC in or BC in. So ultimately, it is a product of three variables A, B, B, C and C in. That is the carry. Now we have sum as well as carry expressions. Sum is A exclusive or B exclusive or C. And therefore take a exclusive OR gate with three inputs and connect all three inputs to it. Output of this exclusive OR gate, you are getting the sum A exclusive or B exclusive or C. Now, in the carry output, we are 3 AND operation. So, connect the inputs to 3 AND gates as shown in the expression. Here, as per the expression, we connect the inputs. First inputs for first gate is AB. So, you are getting A and B at the output. Then for second input, you are applying the input A, C. So output is of this AND gate is AC. And for third gate, we are connecting the input B and C. And therefore you are getting the output B and C. So three terms are generated here. You will see the expression that is ORing of the three terms. So we can use one OR gate and all the three terms and we are getting the final expression for the carry. So therefore, we have implemented the full adder for 3-bit addition. The same full bit adder can be implemented using two half adders as shown in the figure. First half adder will be adding the two bits A and B. Sum S1 and carry 1 will be generated. Then this sum will be added to the third bit by the next half adder with C, and the second half adder will add the sum of the first half adder and C in bit. So ultimately you are getting the sum of 3 bits. and carry from the first half adder and carry from the second half adder is all together, you are getting the carry output, that is the final carry output for the full adder. So we have implemented here logically using this block diagram the full adder using two half adder. In this block, we will substitute the diagram of half adder and you will get the logic diagram for full adder. The expression for sum and expression for the carry remains the same that we have already derived. Now application of full adder. It is used as basic building block for multi-bit additions. That is 4-bit addition or 8-bit addition or 16-bit addition of the binary number or BCD number. It is used in digital electronic systems where arithmetic and logic operations are required like digital diaries, microcomputers or computer systems. They are used as an integral part of arithmetic logic unit of a microcomputer systems. And that's all about the combinational logic circuit as per your syllabus. Let us go to the another type of circuit called sequential circuit. In this sequential circuit, the output of the circuit not only depends on the current state of the logic inputs, but it is also dependent on the previous states of those inputs and also depends on the instance and the sequence in which the inputs are applied. The output of the sequential circuit may also be synchronized with the clock signal. So let us define a clock signal first. Clock signal is basically a logic signal having two states only, logic 0 and logic 1 as shown in the figure. Logic 0 corresponds to 0 volt and logic 1 corresponds to 5 volt. Here, the age changing from 0 to 5 volt is called leading edge, and the age where the output is changing from high to low is called following edge. This leading edge is also called as positive edge and trailing edge is also called as, or falling edge is also called as trailing edge or negative edge. So if you see the clock, we will see that clock is either in low voltage state or it is in high voltage level state. So the low value and high value time is called as level of the signal, and edges where the output changes from 0 to 1 or 1 to 0 is called as edge of the output. When output changes from 0 to 5, it is called as leading edge or positive edge. And when the output clock changes from logic 1 to logic 0, it is called as falling edge or trailing edge or negative edge. Here, time required for one cycle of the clock is called as time period of the clock. And reciprocal of the time period is the clock frequency. Similarly, the high time divided by total time period of the clock is called as duty cycle of the waveform. Now let us see the first building block of a sequential circuit, that is flip-flop. Flip-flops are basically having two stable state. It is also called as a bistable circuit. Here The implementation of the flip-flop using two NAND gate is shown. Basically, these two NAND gates are connected as inverters, that is NOT gate, and B1 input is connected to first NAND gate and B2 input is connected to second NAND gate. And the outputs are cross-coupled. So there is a feedback from output to the input of the next gate. And due to this feedback, the circuit will be going from one stable state to another stable state whenever the input combination changes. That is mentioned here. The state will be changed as per the condition at the input and applied clock if clock is used. If clock is not used, then the output condition will be only depends on the condition of the inputs. Construction wise, it is similar to a cross coupled inverter. There are various types of flip flops available in theories. As per the clocking methods, the flip flop can be level triggered, in which there are positive level triggered flip flops and negative level triggered flip flop. Positive level triggered flip flop changes the state when the logic state of the clock is high. Negative level triggered flip flops changes the state when the clock is in low state here. The another category of the flip-flop as per the clocking method is edge-triggered flip-flop. That is called as positive edge-triggered flip-flop and negative edge-triggered flip-flop. So in this flip-flop, the change of the flip-flop output will only taken place on edges of the clock, that is this leading edge or on trailing edge. That is called positive edge or negative edge. The another class of flip-flops called latches. That is basically the extension of flip-flop. Latches have again two stable state, that is nothing but it is a bistable state circuit, and latches are used to latch the status of the input when clock is applied. When no clock is applied, it will hold the status of the input indefinitely. So new data can be clocked in latches with the clock, and they can be either positive edge trigger or negative edge triggered, or they can be positive level triggered or negative level triggered. Various flip-flop in various categories are listed here. They are either SR flip-flops, they can be clocked SR flip-flop. Clocked SR flip-flop can be further classified as level triggered flip-flop or edge triggered flip-flop. Edge triggered flip-flop can be positive edge triggered or negative edge triggered. They can be JK flip-flops. They can be master slave JK flip-flop. They can be T flip-flop and they can be D flip-flop. T flip-flop is also called as toggle flip-flop and D flip-flops are called as data flip-flop. T flip-flop toggles the state on every edge, say positive edge of the clock, and therefore they toggles in every cycle on positive edge of the clock. D flip-flop latches the data input at the output when the clock is applied and definitely indefinitely hold the data at the output as long as no next clock is applied. Let us see the implementation of the SR flip-flop using NAND gate and NOR gate. First we will see using NOR gate. It consists of two NOR gates. The inputs marked as R input and S input to the two NOR gate here, and the output of first NOR gate is cross coupled to the second input of lower NOR gate, and the output of second NOR gate is connected to the second input of first NOR gate. The R input is also called as reset input, and S input is called as set input. That's why the name of the flip-flop is SR flip-flop. The output of the flip-flop will be always one output is Q and another output is the complement of Q. The expression for this Q output and Q bar output from the NOR gate operation is shown here. So Q output is complement of R or Q bar, and Q bar output is complement of S or Q. So these are the expressions, logical expression for the outputs of the flip-flop. Let us see the operation of SR flip-flop. Let us assume that the initial condition is Q equal to 0. So obviously Q bar equal to 1. When power is first time applied to the flip-flop. Let us consider the first case now. S is equal to 1 and R equal to 0. So we apply, make S is equal to 1 here and R equal to 0. So when S is 1 and R is 0, it is called set mode. So see here, when S is equal to 1, consider the lower NOR gate. So it is not OR. Consider this gate as OR and NOT. So when S is equal to 1, the OR operation output is 1 and complement of it, that is 0. Therefore, Q bar equal to 0. Shown here. When S equal to 1, Q bar will be pulled to 0. When Q bar will be pulled to 0, the second input of the first NOR gate is going to 0 and R is already 0. So both the inputs to this NOR gate are 0. So therefore output of the NOR gate is 0 or 0 complement, that is 1, and therefore Q becomes 1 and Q bar becomes 0. Now consider the second case. When we make S is equal to 0 and R equal to 1, means we want to reset the flip-flop. When R equal to 1, here the first NOR gate output is 0. And when this output is dropping, that is connected to the input of second NOR gate. S is already 0 and this Q output is also going to 0. And therefore, the lower NOR gate output is 0 or 0 complement, and therefore Q bar output is going to 1. And therefore, when R is equal to 1 and S equal to 0, Q output will be 0 and Q bar output is 1. So by making reset input R in logic 1 state, you can reset the output Q to 0. Setting of output means setting it to the logic state 1. And resetting the output means setting it to the logic 0 state. Consider the condition 3. In condition 3, suppose both S and R both are 0. When both are 0, there is no change in the output because the output depends on the previous state of Q and Q bar. So output doesn't change when S and R inputs are same. Let us consider the fourth condition now. When S equal to 1 and R equal to 1, means we want to simultaneously set the output as well as reset the output, and therefore this input combination is an unstable state, and therefore this should not occur in the operation of SR flip-flop. This should be avoided. Otherwise, the circuit goes in the race around condition. Both the output tries to become one, and that is not possible. And therefore, S and R inputs, when both are 1, this condition should be avoided in practice. And therefore, now we will show this SR flip-flop by its symbol. The flip-flop is normally shown by a square box with two inputs S and R and two outputs Q and Q bar. The truth table of the SR flip-flop shown here. Those are the condition of S and R inputs and corresponding output Q and Q bar. And we have seen all the four conditions of S and R inputs. We will fill up this table. When both S and R inputs are 0, the output Q and Q bar remains in the last state. There is no change in output. When R input is 1 and S input is 0, the flip-flop output will be resetted, means Q becomes 0 and Q bar becomes 1. When S input is 1 and R input is 0, we are setting the flip-flop and therefore Q output will be set to 1 and Q bar output will be 0. This is called set state. When both the inputs are 1, this condition should be avoided because this is called the race around condition. When this condition occurs, there will be race in the output to become 1 simultaneously. And therefore, the logic operation of cross-coupled inverter fails. And therefore, this condition should be avoided. Here, the next figure shows the SR flip-flop using NAND gate. Two NAND gates are used. R and S inputs are connected to gate 1 and gate 2 respectively. And Q bar output of second gate is cross-coupled to another input of first NAND gate, and Q output of first NAND gate is cross-coupled to second input of the second NAND gate. The truth table is again same. You can verify from this circuit. When S and R both are 0, there is a race condition now. And therefore, this condition should be avoided in this implementation of the flip-flop. When both the inputs are 0, this NAND gate tries to make the output Q and Q bar both tries to go to 1. And therefore, this is a race condition between the two outputs and therefore should be avoided. When S is equal to 0 and R is equal to 1, here you will get the flip-flop. So you will see when the set out input is 0, the flip-flop output Q will be resetted, and when the reset input is 0, the Q output is set. So there is a complement of this operation takes place compared to the flip-flop implementation using NOR gate. When both the inputs are in logic 1 state, there is no change in output. So flip-flop changes the state when S and R inputs are dissimilar. In this case, the flip-flop can be set or reset by using logic 0 as input. So consider the second row again. When the set input S is 0, the Q output will be 0. So flip-flop will be resetted by using set input 0. And when you have the reset input 0, you will get Q bar output resetted to 0 and Q output becomes 1. So therefore, note the difference between the output between the NAND gate implementation of the SR flip-flop and NOR gate implementation of the SR flip-flop. Now, in general, if we focus on the NOR gate implementation of the SR flip-flop, we have to remember just that when the set input is 1, the Q output will be set to 1. When reset input is 1, the Q output will be resetted. That is for the SR flip-flop using NOR gate. Now, various triggering method used for the flip-flops. We have already discussed this, but let us review it again. The flip-flops can be level triggered flip-flops or they can be edge triggered flip-flop. Means if the flip-flop is changing the state in this positive level here when the clock is logic 1, then it is called positive level or high level triggered flip-flop. Whenever the flip-flop changes the state during low state of the clock, then it is called as negative level or low level triggered flip-flop. Whereas if your flip-flop changes the state on positive edge of the clock only, then it is called positive edge or leading edge triggered flip-flop. Or if your flip-flop is changing the state on falling edge of the clock, it is called as falling edge triggered or trailing edge triggered or negative edge triggered flip-flop. Let us see how clock can be added with the flip-flop. Let us see the NAND implementation of the flip-flop. With this NAND gate implementation of the flip-flop, let us denote the input to the basic SR flip-flop as S dash and R dash. And S and R inputs are additionally passes through the two NAND gates and they are individually ANDed with the clock input. So R dash and S dash input of the first level of the gates depends on the state of the clock, whether it is in high state or in low state. The symbol of the flip-flops are shown here. The first circuit is a SR flip-flop with positive level triggered. Here there is no bubble. In negative level triggered, there is a bubble on the clock input. So if you see these two, we have added the third input in the SR flip-flop, that is clock input CK. Whereas in the third diagram, this one, there is a triangle symbol shown. This indicates the flip-flop outputs depends on the clock input positive edge. So it is called as positive edge triggered flip-flop. And if there is a bubble shown here with a triangle, then it is a negative edge triggered flip-flop. The edge triggered flip-flop output doesn't change for the constant input level either in high state or low state. The edge triggered flip-flops are only changing the status of the output on edges. The truth table of the SR flip-flop with clock is shown as a third input. Say when clock is altogether 0, then S input can be don't care, R input can be don't care. Means this cross indicates the don't care input. Don't care means it can be either 0 or 1. It doesn't have any effect. That is indicated by the cross sign. So when clock is 0 and S and R both are in don't care condition, the output of the SR flip-flop remains constant in the previous state. So there is no change in the output Q and Q bar. When clock is 1 and S and R both are 1, then also there is no change in the output. When clock is 1 and R input is 1, the Q output will be 0 and Q bar output will be 1. This is using NAND implementation. When you use the NOR gate implementation, then when S input is 1 and R input is 0, the Q output will be 1 and Q bar output will be 0. Okay. Now consider the third row. When clock is 1, S input is 1 and R input is 0. The flip-flop will be going in the set condition. When clock input is 1 and both S and R both are 1, then there is a race between the output, and therefore this is the condition which is unstable condition, and therefore this should be avoided. So if you see the first four conditions, when clock is present, clock is absent means it is 0, there is no change on output. When clock is present but both the inputs are 0, then also there is no change in output. And if you see the third row, the flip-flop will be resetted when clock is positive, as well as reset input will be 1. Flip-flop resetted means Q output will be 0 and Q bar output will be 1. Whereas if you consider the next row, when clock is 1 and S input is 1, this flip-flop will be, output will be set to 1, and therefore obviously Q bar output will be complement of Q, that is 0. Set and reset words are normally reference to Q output. When we say that the specific input combination sets the flip-flop, means it will set the output to logic 1 state. Same is for reset. When we say that flip-flop is in reset state, means Q output of the flip-flop will be in reset state, means 0 state. Limitations of SR flip-flop. SR flip-flops, whenever they are level triggered, they are suffered from race condition, means they will toggle more than once as long as the clock level is present at the clock input, and therefore this race around condition can be avoided by converting the SR flip-flop to JK flip-flop or D flip-flop. Let us see simple D flip-flop. In D flip-flop, our SR flip-flop is used using 4 gates. Gate 1 and gate 2 is a basic SR flip-flop. Gate 3 and gate 4 is basically adding the clock input, and the data input D is directly connected to the S input of the flip-flop circuit, and complement of D is used as reset input to the flip-flop. The symbol of D flip-flop is shown here. There is a single input D and Q output and Q bar output, and there is a clock. If there is no bubble on the clock, it is a level triggered flip-flop. If there is a triangle on the clock input, then it is a edge triggered flip-flop. Now here you will see there is a triangle in the symbol, means this is a positive edge triggered flip-flop. If there is a triangle and bubble present on the clock, it becomes a negative triggered flip-flop. If there is no triangle, then it can be positive edge triggered. And if bubble is present, as shown here, if bubble is present only, then it is a negative level triggered flip-flop. The truth table of D flip-flop is shown here. Now there are two inputs to the D flip-flop as shown in this figure, the D input and clock input. When clock input is 0, it is disabled. When clock is 0, the data input is ineffective, means whether it is 0 or 1, it doesn't affect the output of the D flip-flop. When clock is 1 and data input D is 0, then this clock will reset the Q output, means it will set the data input at the Q output, means Q output becomes same as the data input. Now, when clock is 1 and data input D is 1, then output will be set. So from last two rows, you will see that as long as the clock is present, the D output will be reflected at Q, and complement of D is available at Q bar. So ultimately we are saying that this clock will store the condition of data input in the flip-flop. Once the output of the flip-flop is changed, and if we remove the clock from the flip-flop, the output remains in the same state indefinitely as long as the clock is not again made in the logic 1 state. And that's why this flip-flop is called as the data flip-flop, which latches the data input when the clock is in the asserted condition. Now, the JK flip-flop implementation with positive edge triggering is shown here. Again, if you see what is the difference, gate 1 and gate 2 is basic SR flip-flop having input R dash and S dash. Gate 3 and gate 4, they can add the clock input with the two external input. Now they are renamed as J and K. And additionally, in this JK flip-flop, the Q output is cross-coupled as a third input to gate 4, means that is ended with the clock again. And Q bar output of the lower gate number 2 is cross-coupled to the third input of the gate 3, that is ended with clock and J input. The truth table of the symbol of JK flip-flop is shown. Now, if you see here, the additional circuit using capacitance and resistance with a diode is shown. Here, this capacitance and resistance R1 is forming a differentiator circuit, which will convert the square wave clock signal into spikes, differentiated spike. So, output of the differentiator circuit can have only positive spike at positive edge and negative spike at negative edge. Whereas negative spikes means negative voltages are not applied to our logic circuit. We add a diode which rectifies this positive and negative spike, and output only consists of positive spikes. And these positive spikes can be used as a clock. And thus, we have converted a basic SR flip-flop to JK flip-flop with clock edge triggering. The output expression from this circuit can be written as the S dash output, that is the intermediate output, is K, Q and clock complement, and R dash input to basic SR flip-flop is J, Q bar and clock complement. That is basically the NAND operation. You can very well see here. K, clock and Q. That is the AND operation with a complement of by using 4 gate number 4. And this R is CL, J, Q bar and clock, and complement by this inverter. So J, Q bar and clock complement will be R dash. Remaining operation of gate number 1 and 2 is same as general SR flip-flop using NAND gate we have already seen. So let us see the truth table. Now we have clock input, J input and K inputs. Also, we will see that we have cross coupling of Q output and Q bar output, and therefore Qn plus 1 and Qn plus 1 complement, these two outputs are also taken in consideration. Qn plus 1 is the next state of the flip-flop outputs when the input conditions are changed. Now let us see the case 1. When clock is 0 or 1, means if it is having any state, if J and K both the inputs are 0, See here, when J is 0 and K is 0, this is a NAND gate operation. So AND gate gives here 0, complement of it gives 1. So R dash becomes 1 and S dash is also becomes 1. And when R dash and S dash both are 1, then there is no change in the output. We have seen the truth table of SR flip-flop using NAND gate. And therefore, there is no change in Q and Q bar. Consider the second case. Now, if the clock is going down, see here, in our circuit, our flip-flop is only positive edge triggered because we clip the all negative edges and only positive edges are applied. So when clock is going down, there is J and K input in either 0 or 1 state. There is no change in the output because clock is not at all reaching to the gate 3 and 4. And therefore, their output R dash and S dash never changes. And therefore, there is no change in Q and Q bar output again. Third case, when J and K input itself are 0 and clock can be going high, then also there is no change in the output because R dash and S dash inputs are both are in logic 1 state. When they are in logic 1 state, there is no change in the output of the flip-flop using NAND gate 1 and NAND gate 2. The next state that you can very well verify here. Consider J as 0. What is the output of this NAND gate 3? Consider this not AND or AND not. So 0 is ANDed with anything is 0 and not of it. So it is 1. So R dash is 1. Similarly, S dash is 1. And if you refer the truth table of SR flip-flop using NAND gate, when both the inputs are 1, the output will not be changed. Now consider the very important state, that is the fourth state. When J is 0 and K is 1 and clock is also rising from 0 to 1. Then let us assume temporarily that clock is 1, J input is 0, and when J input is 0, definitely R dash input is in logic 1 state. Whereas consider the 4 gate, K is 1, clock is 1, and Q is also 1. So S dash input is in the logic 0 state. When S dash input is in logic 0 state, consider this gate 2 now. This S dash input is 0 means this NOT gate output is 0 and complement of it is 1. So Q bar becomes 1 and Q becomes 0. So therefore, you will say Q bar becomes 1 and Q will be 0. So can we summarize this state? When K input is 1 and clock is applied, you can reset the flip-flop, that Q becomes 0. Similarly, if you consider the fifth case, consider J input is 1 and K input is 0. Now J input 1 means upper gate 3. J input is 1. Consider clock is 1. So two inputs are 1. And Q bar is already 1. So the inputs for the upper gate will be all 1. And therefore, the AND operation results to logic 1 and not of it will be logic 0. And therefore, R dash will be 0. Similarly, if you check the condition of lower NAND gate, you will get S dash equal to 1. When R dash is 0, the gate number 1 output will be equal to logic 1. And when the output Q is in logic 1 state, this cross coupled feedback makes the Q bar in logic 0 state. And therefore, case number 5 indicates that when J input is 1 and clock is applied, the flip-flop will be set in logic 1 state. That is, Q output is made 1. When both the J and K inputs are 1 and clock is changing from low to high, then you will see that the output Q will be toggle to Qn bar state. If it is in logic 1 state, then output goes to logic 0. If it was in logic 0 state, then output becomes logic 1. So toggling takes place when both the inputs are there. You can assume the condition of outputs. Consider Q equal to 1 and Q bar equal to 0. Both J and K are logic 1. And then consider the clock is changed and note down the various status of the signal R dash and S dash and see that what is the change in the output next state. And you will find that when J and K both the inputs are 1 and clock changes, the output will be toggle. Means output changes the state. If it was there in logic 1 state, it becomes 0. If it was in logic 0, it becomes logic 1. That is called toggling. So flip-flop, JK flip-flop toggles on every edge of the clock when both J and K inputs are 1. If edge triggering is not used, means this differentiator circuit is not used, then if it is a high level triggered flip-flop or low level triggered flip-flop, as long as the clock level is maintained, the flip-flop will be continuously toggle when both the inputs J and K are 1. And therefore there exists a race around condition. To avoid the race around condition, we are using the edge triggered flip-flop.